So let's do some problems from chapter 8. So let's see here. We're going to have a flow. Okay, flow. Woo! Squiggly lines. That's my flow. It has a pressure that's equal to 1 atmosphere, and it's got a temperature of 290 Kelvin. Okay. Then what we do is we put a pitot pressure probe into the flow, to measure some stuff. There you go, pitot pressure probe. And this pitot pressure probe, and it measures a pressure of 1.555 atmospheres. Beautiful, perfect, loving it, it's looking good. Okay, there we are. Now, let's see. If we are, and what we want to find is, we're going to try to find the velocity. And let's see here. We're also going to find the velocity using Bernoulli's. And then we're going to find the percent error. Big thing here is remember that Bernoulli is only for incompressible flow. So if we are compressible, which means that my ratio from stagnation density to static density is no longer 1 or within that, then we're going to have bigger and bigger and bigger errors. Okay? So bigger and bigger, bigger errors. Okay, and let's see, was there anything else it told me? Yeah. Well, things we need to ask ourselves. One, are there any shock waves? Is this subsonic? Is this supersonic flow? How do we tell? We're not. We can. But I'll go ahead and tell you. Like, this is one that you're not ready for. It's okay. So the big thing is my pitot probe, it doesn't actually measure pressure, really. I mean, it does, but what it's doing here is it's comparing that pressure to, well, it measures stagnation pressure. So I didn't add that little O in there to see if anybody would catch it. So that's the big thing here. So I measure stagnation pressure, not static pressure. So that's important. So what we get from that is I can say, well, I know what P naught is. I know what P is, and that ratio is 1.555. We can go to the tables. Now, if you go to the isentropic flow tables, so if we go to the tables for isentropic flow, let's put it right here. Don't have this up right this second, but you know, that'd be really good to do. So let's see. And the power of moving magic, here we are, boom, okay. Now, if we are supersonic, then we are going to be above Mach 1. So this first column right here is P naught over P. That's the stagnation pressure to static pressure ratio. And so I'm going to go down to Mach 1, which is right here, and I see that it's 1.893. Now, that still doesn't tell us anything, so we need to look and see what happens. Notice that this is dropping down and approaching 1 as we get to very, very, very low Mach numbers, which makes sense because at that point we're no longer compressible at all. And it gets bigger and bigger and bigger as I get to higher Mach numbers. So since I have a ratio of 1.555, I am actually less than sonic. And the great thing is I can actually look at that and find what my Mach number is right here. If I look in here, I can find 1.555, which is right around here. And that tells me that my Mach number is actually 0.82. So that's good to know. We'll use that information to help ourselves out. Okay, so this is actually less than 1.893, which means that I am subsonic. Okay? And then from the tables, I found out that for P naught over P, which is equal to 1.555, it is going to be a Mach number that is equal to 0.82. Cool beans. That's all from the tables. The tables are amazing for this. Always go to the appendices. I should say the table and the appendices. Now, using that, let's go through this and calculate velocity. How do we do that? We're doing this right now in the compressible flow way. Compressible flow uses Mach numbers to calculate the speed, my velocity. And so I do that by remembering that my Mach number is equal to my velocity over the, I almost said area, over the speed of sound. And I know how to calculate speed of sound as well. So speed of sound is equal to the square root of gamma r t, right there. So I can then plug this into my calculator, and I get, let's see here, that's 1.4 times 287 times a temperature of 290 Kelvin. Okay. And that's a velocity of 341.35 meters per second. That's the speed of sound. I haven't got the velocity yet. Because I'm not moving at sonic speeds, I'm moving less than that. I'll be a ratio of this, or a fraction of this. So 0.82 is equal to my velocity over 341.35 meters per second. And I can then solve for this, and I say that my velocity is equal to 0.82 times 341.35, or that it's equal to 279.91 meters per second. Okay, so that is the accurate velocity. That is correct. That is taking into account compressibility effects, and we're all good to go there. Now let's do this differently. We're going to just use Bernoulli's now and see how it goes. We're going to compare these two. So Bernoulli's still works out fine. And we're first going to have to know, let's see here, what is Bernoulli's equation? Do you remember it? I'll find it for you, man. Don't worry. I know you got it in there. But see, the pressure plus 1/2 rho V1, this is 1 squared, is equal to P2 plus 1/2 rho V2 squared. The thing is, since we have two pressures here, so we have our static pressure and our stagnation pressure, what's our velocity when we're stagnant? It's 0. So this guy over here, we say that's equal to 0, and P2 we're just going to say is equal to P0. So I want velocity, so I'm going to rearrange and get velocity then. So I say, okay, 1/2 rho V squared is equal to P0 minus P, and then V squared is equal to 2 times P0 minus P, all divided by the density. And then finally, if I take the square root of that, I get my velocity. So my velocity is equal to the square root of 2 stagnation pressure minus static pressure all over the density. So that's not too hard to do. We have our stagnation and static pressure. We don't have our density, so we'll just use the ideal gas law to calculate the density. And that's not a good thing to do because air is compressing. If it's compressing, it's no longer an ideal gas. So pressure is equal to density RT. Therefore, density is equal to the pressure over RT. Looks good. And so I can then plug that in there. As a note, 1 atmosphere is equal to 1.01 times 10 to the 5th pascals. We're going to use that conversion here. I'm not going to go ahead and put it in there. I'm just going to put in, since it was 1 atmosphere, that is 1.01 times to the 5th. So this will be equal to 1.01 times 10 to the 5th, all over R, which is 287, times the temperature, which is 290. And that comes out to be a density of 1.21 kilograms per meter cubed. We could have kind of just used the basic one for air that you find online, but we did the full steps here, and this is, slightly more accurate for our problem. And so plugging all of that in, I can then calculate my velocity. I say, okay, my velocity is going to be the square root of 2 times 1.55 minus 1. That's atmospheres, though, so I need to convert it. So I'm going to go ahead and multiply by that 1.01 times 10 to the 5th. That is Pascal per atmosphere. So I got everything in pascals, which is what I needed in. And on the bottom, I'm going to put my density, which is 1.21 kilograms per meter cubed. If you're wondering how meters per second comes out of this, I could show that to you, but the biggest thing is if you're in base metric units, it typically works out just fine, at least for this class. And what I get is my velocity is equal to 303.95 meters per second. Okay, so I got my second velocity here. This is Bernoulli's. My first velocity was 279.91. So the compressible one, V is equal to 279.91, and that one is correct. So we can see here that there is a difference. Now how big is that difference? Well, let's calculate percentage error. So that's simply the bad one, 303.95, minus the correct one, 279.91, all over the correct one, 279.91. And you have to do it that way. So it's bad minus correct over correct. Okay? And then you multiply it by 100 to get it in percent. And we would get that this is equal to 8.59% error. So, not the best. We got error there. Ooh, not fun. Not fun. But this is important because we need to realize that there are issues with how we were doing this problem. There are issues with it, so this will help us out with that. Okay, good so far? Cool.